Hi, this is Mrs. Basden, and today we're going to talk about the wave nature of light, which is section 6.1. So in this chapter, we're going to talk about the structure of the atom, and we're going to focus specifically on where the electrons are. The reason that's important is because the electrons are what determines where the electrons are, how many electrons an atom has, determines how an atom behaves. So when we talk about electrons, there are two different ways electrons can behave. You can describe or be described. You can describe electrons as having wave properties, but you can also describe electrons as having particle properties. So in this first section, we're going to look at electrons and how they have properties of waves. So to understand that, we have to talk a little bit about the structure of a wave, the different parts of a wave, and then how that relates to electromagnetic radiation. So if you look at the diagram here, it shows the wavelength of a wave. So light travels in waves, and electrons behave in that same way. So if you look at the wave there, the distance from peak to peak on a wave is called the wavelength. So that's basically how long the waves are. So that distance between there is called the wavelength. And if you notice, it's notated with the Greek symbol lambda. The other term we can use, and the other way to describe a wave, is to describe its frequency. So the frequency is how many waves pass a point in a given unit of time, or usually it's per second. So this is described as frequency. And if you look on here, the frequency is notated with the Greek letter nu, which is that little thing that looks like a V. If you have waves that are traveling at the same speed, which we're going to, at this point, assume they all travel at the speed of light, the longer the wavelength, the smaller the frequency. So wavelength and frequency are inversely proportional. If you have a longer wave, you're going to have less pass a point in a given second. If you have a shorter wave, you're going to have more pass a point in a second. Okay, so this brings us to electromagnetic radiation. So on the chart here, and you guys have seen this before in Honors Chem, these are all the different forms of electromagnetic radiation. And if you notice on here, they all travel at the same speed. So they all travel at the speed of light, which is notated with the C. And that value is 3 times 10 to the 8th meter per second. But if you look on here, you can see things with a very short wavelength, which are over on this side, have a very high frequency. Things that have a very long wavelength over here have a much lower frequency. You also notice that if you look at those things and kind of relate those to what they are, gamma rays, X-rays, these are things that are more dangerous, things that have a higher frequency, whereas over here, these are things that are not as harmful. So the higher the frequency of something, the more potential it has to damage our cells, which is why those things are dangerous. The other thing you'll notice is this real tiny section here is visible light. So visible light is just a very small part of the electromagnetic radiation, and that's the only part of the spectrum that we can actually see. So they've expanded that a little bit so you can see the colors, and then down here, these are given in nanometers. So instead of meters like they are on the chart, they've changed these here to nanometers. And you'll see that the wavelength corresponds to the color of light that we see. So knowing that the frequency and the wavelength are related, and knowing that they all travel at the same speed, we can use this relationship C equals lambda nu. So the speed of light equals the wavelength times the frequency. So again, this stands for wavelength, and the nu stands for frequency. Okay, so if we have one of those values, because this one is a constant, we are able to calculate the other one. Okay, so let's look at a couple examples of these. So this one says, the yellow light given off by a sodium vapor lamp, so these are old-fashioned street lamps where actually the light came from a sodium vapor, has a wavelength of 589 nanometers. We want to know what is the frequency of this radiation. So just like all of these problems, I'm going to list what variables I'm given. So I'm given the wavelength, so I'm given lambda, and it's 589 nanometers. The other value I know, because we're going to assume they all travel at the same speed, is the 3 times 10 to the 8th meters per second, which is the speed. And what I'm looking for is the frequency. Now, the one thing you have to be careful of here is you have to watch the unit on the wavelength. So the unit in my speed is meters, but my wavelength was given in nanometers. So I'm going to have to do a conversion here. So the conversion we're going to use is 1 nanometer is 1 times 10 to the negative 9 meters. So that gives me 5.89 times 10 to the negative 7 meters. So you have to convert that and make sure that your unit and your speed and your unit and your wavelength is the same. So now I have all that. All I have to do is put these into my equation. So I'm going to substitute my values in here. And this is meters per second. My wavelength is 5.89 times 10 to the negative 7th meters. And then I'm solving for nu, which is my frequency. So when I solve for nu, I end up with 5.09 times 10 to the 14th. Now my unit here, if you notice, meters is going to cancel out and you're left with 1 over seconds. So I can report this as seconds to the negative 1. That's a notation you'll see a lot of times in AP. The other way I could report it is hertz. So hertz is the unit for frequency, and that is the same as 1 over seconds or seconds to the negative 1. So any of those units would be acceptable for frequency. Hertz, 1 over seconds, or seconds to the negative 1. Okay, let's try one more. This one says we have a laser that's used in eye surgery. It has a frequency of 4.69 times 10 to the 14 hertz, which is the same as 1 over seconds. We want to solve for the wavelength. And just like last time, we know the speed is 3 times 10 to the 8th meters per second. Okay, so I'm going to use my same formula. C equals lambda nu. I have my speed, 3 times 10 to the 8th meters per second. Lambda is what I'm solving for this time. I have 4.69 times 10 to the 14 hertz. I solve for wavelength, and this gives me 6.40 times 10 to the negative 7th meters, because this hertz cancels out the 1 over seconds, so I'm left with meters. And then if you wanted to, you could change this even to nanometers by using the conversion we talked about before, and that ends up being 640 nanometers. You don't have to report it in one versus the other unless the specific problem is asking for it, so you can report that either way.